star.
A, right, okay.
But I was thinking about the origin of the rapidly rotating star.
And I thought, a few paragraphs later that they sort of mentioned that it might have come from a collision of two stars.
A natural path to making such a star would be the merger of two less massive stars that are born in a tight binary.
Right.
But still the rotation cannot be that large, right?
But they're then talking about, so it's one star at the end. So it's not that there are two stars, both of which have black holes that have formed and merged. Once the two stars merge, the merger product will be endowed with rapid rotation.
Sure. With one core only. Because
With
they
one
assume
core.
that the core has merged. And then somehow, I'm assuming that they assume that the core starts collapsing and then the rotation support gets
Yeah,
sufficiently high to elongate the
you
core
get a
itself.
dumbbell
Right.
Okay.
configuration.
And then that collapses to a black hole, then they merge.
Yeah,
I mean, that, to me, that's the salient feature, or the important feature here, is that you create the black hole binary mere seconds before you have a merger.
That's definitely the point.
And even then, that sounds bad, but if you create that 3 seconds before the merger, you've got a second and a half before it shows up in the LIGO band. So it's not like you would see something in LIGO where there's nothing and all of a sudden poof, instant inspire. So I think since I'm running low on my hour.
So the clear-cut prediction of this model is that there's no sources like this that will be observable by LISA. At all.
Right, this would
Yeah.
kill any LISA sources.
This
Yeah.
is the point.
Yeah. And actually, well, no, the mob scenario would still form LISA sources,
But not this one.
but not this
Not
one.
this one.
So that's, and what I want to finish with, although I like what Massimo pointed out, because that's sort of why I'm interested in this, is not the event, but the fact that this implies there's a pile of LISA sources.
Maybe, unless.
Unless, yeah, but, okay. I try gracefully to go from sanity to,
So, if you had, if you had a binary which was formed inside a dense cluster, well, let's say it was formed under the Bolshinsky scenario, but separation was much larger than 50 solar radii, and then, due to interactions with other lighter things, it gradually became harder. Would you class that as field or dynamical, or?
I would call it dynamical, but I'll let Cole make that decision.
yeah,
The idea is that, so you have a primordial binary in a cluster.
yeah.
That primordial binary survives but hardens.
I think that's dynamical. I mean, it's obviously a matter of taste, but I think the way I would just say it is that what Matt is talking about here is an isolated binary. So a binary that never comes anywhere near any other stars. And the distinction between that and something dynamical, I think you could even make the argument that a binary that has a tertiary companion and no stars nearby would involve dynamical processes.
Yeah. But I do have a question, and I thought what Tom brought up was kind of interesting, though, is that would the spins get scrambled in that scenario?
The spins get scrambled, but then there's the question of what the initial spin is.
Right, but I'm saying that, because one of the things that people talk about is the possibility of distinguishing between dynamical to field by whether the spins are aligned. But of course, that depends on kicks. But the question would then be is if, I guess maybe in the dynamical formation, if it's hardened,
Yeah.
you can probably also still get effects that would change the orbital plane or
I
not?
think it's almost guaranteed.
Yeah,
I mean, essentially, everything comes along. Changing the semi-major axis, the eccentricity, and the orbital inclination are kind of part and parcel.
right. And so that's a possibility that you would then scramble the spins. So that's another possibility or thing to consider. But yeah, Cole is going to talk about the dynamical stuff. But I do want to wrap up, I mean, if I can go another couple minutes, because I'd like to talk a little bit about the LISA sources. Because this is the part I think is really interesting. Alberto Cesana came out with a paper which I think is, and he'll agree, at least I hope he'll agree, otherwise he'll be here on Thursday to tell me I'm wrong, that it was somewhat optimistic. And part of that, though, was, and he's perfectly clear on it, is the assumptions he made. He made that looking for possible LISA sources, that you had 5 million kilometer arms, that you had 5-year observation integration, that you had 3 arms on LISA. For those of you who don't know details about LISA, 3 arms on LISA means 2 independent detectors. Okay. So if you think about those combinations of the 5 million kilometer arms, which gives you better sensitivity at low frequencies, that the 5-year integration time gives you a square root of 5 increase in signal to noise ratio. Using 2 detectors gives you a square root of 2 increase in your signal to noise ratio. So that's a way for that's somewhat optimistic in what your detector sensitivity is. I've done something similar, but it was a few years back. So and I always like to at least advertise my former undergrads. So there's me, Jesus Hinojosa, Alberto Manta, they did this work with me as undergrads, and then Chris Belczynski. And what we did is we looked at what was, this was, I think, 3 years ago, 4 years ago, so I'm safe to say this was before I knew about the LIGO source. but basically this was asking, if you allowed there to be the massive black holes that Chris Belczynski was predicting also a while ago, talking about low metallicity systems, if you allowed there to be massive black hole binaries, how far could LISA see them? Because for most stellar mass binaries, LISA is pretty much confined to the galaxy, to the Milky Way. But if you go up to, say, 280 solar mass black holes, how far away could you see those with LISA? I used a less optimistic LISA formulation, 2 million kilometer arms, single detector, 1-year observation. And it turned out that if you just have smooth or even distribution of masses in orbital periods, that about 50% of binaries with masses in the range of 30 to 40 solar masses would be detectable out at 20 megaparsecs. That 20 megaparsecs doesn't sound that far, but it gets us to the Virgo cluster. And there's a pile of galaxies in the Virgo cluster. And this is particularly appropriate, so I'm really hoping that Cole will be incredibly optimistic about how you make these guys in globular clusters. But there's a elliptical galaxy, I think it's M87, 10,000 globular clusters. So you could produce these things in globular clusters. And if you could, they might be visible out to the Virgo cluster. And this starts to be really cool when you think about it. Right? Now, because you could start using LISA to map distances to a cluster of galaxies. So I just want to talk a little bit about some estimations. I want to make sure I get my powers right. Oops. So, I want to look at the frequency evolution of a black, or any binary under gravitational waves. The frequency evolution looks like that. This K0 is some hideous thing that involves 96 fifths and some pi's and g's to the 5/3 and c's to the 5th, and the chirp mass. Now Thomas talked a little bit about the chirp mass. Another way of writing the chirp mass that I think sometimes astronomers like better is it's the reduced mass to the 3/5 power times the total mass to the 2/5 power. That's another way of writing the chirp mass. So from here, what we can say is let's look at the fact that we had one event merge. Okay? That's the LIGO event. And that LIGO event, we have an event rate, roughly speaking, of somewhere between 2 and 400. And now I can go backwards and say if I get one of those, between 2 and 400 of those per cubic gigaparsec per year, okay, that's my rate. Let's go back and say how many of them are in the LISA band. And we can get a number density per frequency interval. And the number density per frequency interval, which I'll call dn, eta is my event rate. So you pick your favorite event rate out of LIGO, divided by this K0, which depends on your chirp masses. Then it's just f to the minus 11/3 df. It's not particularly challenging math. And so you can take that and integrate. If you're lazy, like I am, you just assume everything is 30 solar masses, and then you don't have to worry about an event rate that is also depends on mass. So you integrate backwards from here, and it's a really cool thing. If you say, let's go out to 30 megaparsecs, because that's the distance to the edge of the far edge of the Virgo cluster, assume all of your stars are 30 solar masses, and go back and figure how many of them are going to be in the Lisa band, and by that I mean above a millihertz. I'm going to let it go all the way up to an infinite number of hertz, or merger, because actually once you get up to about 10 to the minus 1 hertz in the Lisa band, you have less than a year before it merges. So, and so that means that most of this number that I'm going to get are going to be between 10 to the minus 3 and 10 to the minus 1 hertz. Really cool feature. So I'm going to write this down to make sure. We have some F naught, which is our lower frequency, of about 1 millihertz. Assume that all the masses, so that all the masses are 30 solar masses, so that the chirp mass is about 24 solar masses. And we use the event rate eta. And what happens then is the total number of binaries out to, or the distance, is 30 megaparsecs. The total number in that volume, all the numbers work out right. So effectively, granted, the units aren't right here, so it's just number. Don't worry about the units on here. But basically, that means that given the LIGO event rate of 2 to 400, there are 2 to 400 double black hole binaries with or frequencies above a millihertz out to the Virgo cluster. Now, that might make you think, well, that's kind of small, especially since only 50% of them are going to be detectable, so that means it's somewhere between 1 and 200. But remember, this was assuming them all having a chirp mass of 24, meaning they're all 30 solar masses. But if you have slightly lower mass black holes, those slightly lower mass black holes will evolve slower, and if you want to keep that same event rate, you're going to have more. So you can think of this as a lower bound.
Okay. Well, sorry, you're gonna go on, but 1 millihertz is gonna be eaten by white dwarfs.
No. I mean, it's on the edge, yeah, but 3 millihertz won't.
That's a significant drop.
A little bit, yeah. Because it does go as after the 8 hertz when we do the integration.
Yeah.
Yeah. I mean, it's a moderately significant drop, but again, it may not be eaten by white dwarfs in the sense that Lisa can be pointed a little bit.
Well, what's the amplitude? Because this is the total number of.
Oh, yeah.
sources.
Well, that's true. Well, what I did was through just a sort of Monte Carlo with a whole range of, I mean, of all the frequencies, but the different masses and different distances, different orientations, that half of them, roughly 50% of them would be detectable.
So,
And with a signal to noise of 10.
So a Lisa instrumental sensitivity alone of SNR 10.
And that's the average. I mean, or that was my cutoff. So half of them will be 10 or better. And that again depends on sort of orientation and stuff like that. So the cool thing about this, then just to sort of wrap up, is that this is, to my mind, it's a conservative estimate. That's somewhere around, I would say, more than 0, perhaps less than 1,000. If you put a gun to my head and told me to make an estimate, I'd say maybe 20 to 100 is what I would think. That you would have sources detectable by Lisa. Now the last little thing I want to mention, and I like sort of thinking about it in this way, going back to how they measured the distance to the GW 150914. The way you measure the distance, and I was like thinking of this from a gravitational wave point of view, treating it as astronomers, is that F dot, which is something you can measure in gravitational waves, the chirp, okay, is telling you the rate at which energy is being lost by the system in gravitational waves. It's the absolute magnitude, modulo the chirp mass. On the other hand, the H, the strain amplitude measured by the detector, is your apparent magnitude, modulo the chirp mass. And it turns out they come in exactly the same form, so that the distance that you measure, there's assorted G's and C's and things, looks like F, and I want to make sure I get the power right. It is, yeah, F dot over h times f cubed. So if you can measure f dot reasonably well and h reasonably well, and actually the easiest one is f. F is pretty well measured by Lisa. These two maybe not so much, but again, remember these are black holes, so they chirp. So you can get a pretty significant chirp out of this. That you can measure the distance to the source in the Virgo cluster, so you get a redshift independent distance measurement. The only problem is that you have the error box of Lisa. On the other hand, assuming these are reasonably loud, which means we might cut down to only 2 or 3 really loud ones that you could get, that if they're reasonably loud, the error box might be as small as a square degree. Square degree maybe doesn't sound that small, but if you look at the Virgo cluster and you assume it's one of the guys coming from one of the globular clusters in M87, that's pretty much the only thing in that box. So you could start measuring distances to individual galaxies in the Virgo cluster independent of redshift, which I think is an incredibly cool thing you can do with gravitational waves. So, and I think that's probably a good point to end.